Okay, hello sis 11. Welcome to lecture 10. For lecture 10, we'll have more recursion. This should be the last lecture that focuses on recursion for sis 11. So, we'll encounter more recursion problems and we'll discuss something called mutual recursion. So, let's dive in. Quick recap of what we learned so far from previous lectures and lab lectures. So, from the previous lecture, we learned test driven development, where sometimes it's a good idea to start writing tests first for the code that we're going to write. And the main thing that we learned from the previous lecture would be cumulative recursion, or another name we used for it was loopy recursion. So, in a cumulative recursion, we store an extra argument or extra arguments in our recursive functions, and that's where we build up our solutions step by step. I think we did not cover these last three items yet. This will be covered in a lab lecture, so maybe later when we have labs again, aside from the mock hope and hope 1, then these three things will be covered. Okay, let's have more recursion examples. So we'll start. We have this first problem called ordered partitions. Ordered partition. So you have an integer n and you want to cut it up into several integers whose sum is equal to n. And the problem that we want to solve is we want to find all the ways n can be decomposed as a sum of positive integers. When we say ordered, the ordering of the integers matter in terms of uniqueness. So if, for example, if we have n is equal to 5, these two orderings are distinct. The order matters. The order of the integers or the summands, the things that you sum together, are their order matters. Okay, so we want to return a frozen set of tuples. Alright, so find all the ways. So we're going to be enumerating all the possible ways we can divide n into a sum of positive integers. How do we do this? So we want to define a function called ordered partitions. Takes a single argument n. So in the spirit of test-driven development, we can write an assertion before even writing our function. So let's try to start with that. Ordered partitions n, then dot. Oops. Assert ordered partitions of 4 is equal to the following: 1, 1, 1, 1. Okay. We need a frozen set. So we put the frozen set there so that we can generate all the partitions in any order. But this is one way to order them. So we start with all ones and then twos, 1, 2, 1, 1, 3. You can see that all of these sum up to 4. And finally this one. Okay. So we have an assertion ready to test if our code is correct. How would we do this? Let's try a cumulative recursion or loopy recursion. So with loopy recursion, we want to build our solutions step by step. So instead of doing wishful thinking, we will build our solutions step by step. So we start with these smaller cases and then, or well, one thing we could do, I guess it's still wishful thinking, but or rather we are maintaining a partial solution and then we'll build it up as we go through the recursion. So we are doing partitions here. So what we could do is we could choose the first partition and then recursively partition the rest of partition what's left. Okay, so if, for example, if we chose 1 at the beginning, then we can recursively partition 3. So that's the idea. This is still wishful thinking. Okay, so alright, we'll define our loop recursion as follows. This is just the initial call to our ordered partitions function, but for the accumulative recursion function, we are going to use these arguments. So pref contains the partitions that we have accumulated so far. N would be the amount we want to partition, and F stands for the size of the first partition, or the starting size of the first partition that we will take from N. Okay. To summarize, this function will return a frozen set containing all partitions of N, where the first one is at least F, and pref is prepended to each partition. Okay, let's try to write down this function. So in terms of the starting function call, we want to partition N, and the first partition is at least 1, size 1, and initially we have nothing to prepend, so we start with an empty partial solution. What does the value f allow us to do? Well, okay, and f ref. So for a given f and n, we have two choices. Either we take a partition of size f, or so if we take a partition of size f, that's that would correspond to this function call, right? So for example, we are, okay, let me illustrate. So let's say you want a partition. Okay, let me fix this sketchbook. Okay, give me a moment. Okay, let's try it this time. Okay. Uh-huh. Alright, so if you want to partition 5, let me just call this OP, ordered partitions. 5, 1, and we start with an empty partial solution. So we could choose to partition. We could take the first partition of size 1, or we could move on to the other partition sizes. So could have two choices, and if we combine so we can take the partitions of size 4 where the size of the first partition is at least 1, and then we already put 1 here. So we chose the first partition to be of size 1, or so all the results of this we want to get, or we could get all partitions of at least size 2. Okay, so for the current size of the first partition, these are our choices. Either we take that as the size of the first partition, or we move on to the next size, or the size of the first partition is now at least of size 2 instead of at least size 1. And both of these two recursive calls, by wishful thinking, return frozen set, so we get the union of these two, or something like that. So return a union of these two. Does that make sense? So for example, let's check the slides again. So, sorry. The partitions, this is 4. Okay, doesn't matter. Let's use 4 as an example. So this is 4. It should be 3, 4. Alright. Okay, so the partitions of 4 that have 1 at the start as the first partition would be these 4, and then the other partitions that will partition 4, but the smallest size of the first partition is 2, would be the following. Okay, so both of them, and the two sets are combined, they constitute all of these solutions, or all the partitions. So it seems correct. Our wishful thinking seems complete, or we are capable of enumerating all possible partitions using these two choices. So let's write that down. Okay. So ordered partitions of n minus f. We will choose f to be the size of the first partition, and then we start again at the size 1 for n minus f. Pref is now, so we want to build solution step by step, right? So if pref contained something, put it at the beginning, and then we add f here, since we are adding f to the partitions that we are building. Okay, so cumulative recursion style, we are building the solution one step at a time. So these are the previous partitions that we already got, and this is the next one. So this is a frozen set. We union that with the other choice, where we skip the current size f for the first partition, instead add 1 to it. So this, and then pref remains the same. Okay. And we return this. Maybe I should do this. Okay. So the union of these two frozen sets should contain all the results of contain all the ordered partitions for n and f. Alright, we need some base cases. Well, if n is 0 already, then we return that means we no longer have to partition anything. Return a frozen set containing just ref. Right, since this would be one of the partitions. So eventually we'll run out of n, and then if n is equal to 0, that means we are able to partition n perfectly using positive integers, and we found a valid partition. So pref contains a valid partition, we return a frozen set containing that single ordered partition. Okay. Otherwise, we have to account for cases where it's impossible to find a partition. Notice here, we are subtracting from n, so it's possible that this value is negative. Okay, so if n is negative, we cannot, there are no partitions to speak of. Or for this choice, we are increasing f by 1. If f exceeds the value of n, then we can no longer partition n where the first partition is size of at least f, if f is greater than n. So you can do it like this. F is greater than n, or n is less than f. Then return a frozen set containing nothing. Okay. There are no partitions for when this happens. Okay, let's try this with the assertion. Alright, let me visualize. For example, alright, let's try to process this further. 3, 1, we'll call on 2, 1, 1, 1, and 2, No. 3, 2, 1. Right? Let's try to expand this one further. This will call on 1, 1, 1, 1, 1, or 2, 2, 1, 1. This one, so I'm just trying to verify if this works. This will use 0, 1, 1, 1, 1, 1. So this is done here. Or it will go to 1, 2, 1, 1, 1. Alright, so for this case, it's already done. N is 0 and we have a valid partition here. But for this case, f exceeds n and there's no way to partition 1 where the size of the first partition is at least 2. So this will return a empty frozen set. So it seems that our base cases will work. There's also the case when, actually no, yeah, so that will work. Okay, let's try running the code, see if it works. Okay. Alright, the assertion holds and this is working. Of course, you could also write this using regular recursion or the non-accumulative recursion. How would that look like? You would also do this idea, but use wishful thinking more directly instead of building the solutions one by one. From bottom to top. Let me try doing that. Let's just call this OP. If I already have the ordered partitions, I think it would be the same. So it would be something like alright, so okay. I think it's more difficult this way. So let's stick with this. Okay, so we have ordered partitions like this in a cumulative recursion fashion. Okay, let's go to the next problem. So here's how you implement that. Okay. Next, we have unordered partitions this time, where the order of the sum does not matter. For this one, you only want to count the number of ways instead of enumerating all the unordered partitions. So given an integer n, find the number of ways it can be decomposed as a sum of positive integers. Here's an example, and we have assertions here. So reordering the elements does not matter. For example, here 1 plus 1 plus 2 is the same partition as 2 plus 1 plus 1. So we assert that partitions 4 is equal to 5. Let's do that. And you can see the valid partitions on the bottom. Okay, how do we implement this? Well, let's try some wishful thinking. By wishful thinking, how many choices do we have for the first partition? So we need a positive integer, so could have 1 up to n, right? So looks like the answer is like this, right? For example, we're partitioning 4. We're counting our partitions where we are partitioning 3. That means we chose 1 as the first partition. For this one, we chose the first partition to be of size 2, and so on until we choose the first partition to be of size n. So let me just illustrate that. Let's say we're partitioning 3. Just call it 3. So if we choose 1 to be the size of the first partition, then this would mean we are partitioning 2 for the rest of the partition. If we chose 2 to be the first partition size, then we are partitioning 1. We are left with partitioning value 1. And if we chose 3 to be the size of the first partition, we are partitioning 0. This could be our base case. Partitioning 0 is equal to, there's only one way to partition 0, and that's 1. But we encounter a problem. What's the problem? If we go through here, we have 2 choices now for P2. We chose 1 to be the first partition, we get this. And we are left with P1. If we chose 2 here, we have 1, 2, we have partition 0. Okay, seems like there's no problem there. Let's continue. P1, we only have one choice, excuse me. This is P0. So this evaluates to 1 also. Okay, but how about this? 2, 1, we only have one choice here. That's this partition. 2, 1. Then we partition 0, so this is equal to 1. But we have a duplication here. We mentioned that order does not matter. These are unordered partitions. But we are double counting if we are using this sum of where P of n is equal to P of 1 plus P of n minus 1 plus P of n minus 2 plus dot 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 plus P of 0. We are double counting, so this is not the correct way to count the number of unordered partitions. We are double counting here. And it seems we can't fix this problem with this formulation because we have to keep track of if we already use a 2 or we already use 2 2s or something like that. So it seems we're stuck. What can we do to solve the problem? It seems that we need additional information. Just the value n is not enough to express what we are trying to do. Okay, so let's solve a harder problem or a more general problem. In this case, we add another parameter. We define partitions n m to be the number of partitions of n where all summands or all the partitions that we will use are at most m. So there's a limit to the size of the partitions. At most m. How does this help us? Well, to solve the original problem, partitions n, this is just a special case of partitions n m. The size of the summands is at most n itself, which makes sense. Since one valid partition would be n itself, so the size of the summands are at most m. Or at, yeah, where m equals n in this case, which corresponds to our original problem, partitions n. So how do we formulate this? What's the wishful thinking? Well, we could, for a given n and m, if you choose the current m to be the first partition, okay, so let's see. We can split our decision into two cases. If we choose, we can choose the largest element of the partition to be less than m. So that means we don't use m right now, or yeah, we don't use m in our current, in one of the partitions, so we skip m. So set m to m minus 1 and n remains the same. So this is a sub-problem. Or we could set m to be the largest element of the partition and partition the rest of what remains. So that's n minus m, and we are going to partition that using m again. Okay. And you can verify that these two account for all possible partitions. So this says all the partitions, the number of partitions of n where the partition is less than m. So it does not include m. So the summands are at most m minus 1. And here, the largest element of the partition is equal to m, so we are counting the number of partitions for n minus m, where the largest element is m, because we already use m in this partition. Okay, so these two, when combined, account for all possible partitions. So we have the following equation. So let's write that down. Let's go back to our example here. In the case of partitions 4, all the partitions that have a maximum summand less than 4 are these partitions. And all the summands, all the partitions that have maximum summand equal to 4 are these partitions, only one partition. Okay, so they constitute the whole set. Let's say we have partitions 3. So recursively, that would be 3, So partitions that have three partitions of 3 with maximum 3 would be just this, and partitions of 3 with maximum at most 2 would be these, right? So okay, so you can see how it works. So let's write the recurrence down in code. Turn partitions n. So let's write the recurrence first. Partitions n minus 1 plus partitions n minus m. Of course, this is recursion, we need a base case. Let's see where our smaller problems lead us. So we are subtracting from m becomes smaller, and n also becomes smaller. So when are the cases where we have problems that are easy to solve? If n is equal to 0, what's the answer? There's only one way to partition 0 regardless of m. No, sorry. If n is less than m, then there's no way to partition n where, no. What does m mean again? The size of the largest summand. No. If n is less than 0, then there's no way to solve that. You cannot partition a negative value. What else? If n is equal to 0, what does that mean? It means we're able to partition. So that's one partition. I think we need to add a case here. If m is equal to 0 or less, if m is equal to 0, there's no way to partition any n. So let's say if n is positive but m is now equal to 0, then that's not a valid partition because the largest partition size is 0, and that's no longer a valid partition using positive integers. So this makes sense. Let's see. Okay, if n is 0, the answer is just 1. If n is less than 0 or m is less than or equal to 0, then the answer is 0. Why does this matter? Because, of course, if n is less than 0, then there's no partitioning. If m is less than or equal to 0, then no matter what n is, we can no longer create a valid partitioning using positive integers because the largest summand is at most 0 or less than 0. So this is 0. Okay, let's try. This should return 5. Alright, it works. Okay. Can write a version of this that builds up the solutions, but we can leave that as an exercise. Okay. Okay, so the visual thinking for these problems can be tricky. The lesson for the partitions problem would be sometimes you need to solve a general problem to solve your specific problem, which is weird. We solve a more difficult problem to solve our simpler problem. Why did that work? Seems paradoxical. Roughly, it worked because we're doing wishful thinking on a more general problem, which means we have more smaller problems that we can use. So we're now able to use these, and the extra information allowed us to count the partitions uniquely, which we could not have done with just a single parameter. Okay, so we are able to use more smaller problems. Alright, let's see more quick examples of more recursion problems. Given an R by C grid, generate all paths from bottom left to top right. So let's quickly write this. And this would be the asserted answer for a grid of 3 rows and 4 columns. Let's write all paths. So here, a pipe corresponds to a vertical move downwards, and a dash corresponds to a horizontal move to the right. So only movements allowed are up and right. How many paths are there from the top left? From the bottom left to the top right. So if we start from the bottom left, only movements allowed are up and right. Okay. Sorry, from bottom left to top right. Alright. Sorry. RC. Okay. RC. So if we can go up, so the visual thinking would be going up is equivalent to solving the similar problem but with one less row. Going to the right is similar to solving the problem with one less column. So let's just take care of those cases using the base case. Let me illustrate what I mean. So if we are solving all paths 3, 4, so the grid looks like this. 3 rows. Okay, so we start from the bottom left, we want to go to the top right. If we go to the right, it's as if we're solving this smaller problem, but we already made a move of dash, or we went to the right. Or if we go up, we are solving this smaller problem instead. One row less. And this constitutes a move of something like that. Okay? So a pipe going up. So how do we generate all possible paths? Okay, how do we do this? So if we go up, we add this plus we're gonna add an up movement plus S for all the solutions in all paths we went up, right? R minus 1 C, right? Union with, let me do this. So if we go up, we are recursively solving all paths for the grid with one less row. And we want to put this in front of all the possible paths for this smaller grid, right? We're adding one step, and then whatever the solutions for these are, we're putting the initial up movement at the start of each string. Okay? Union that with, okay, going to the right, plus all the strings for, plus S for all the strings in all paths are minus 1 column. Okay. Of course, this does not check if we go out of bounds on the grid, so we need those base cases. First, we need the base case when we no longer need to do anything. So if RC is equal to, if there are no rows and no columns, or sorry, there is one row and one column, we don't need the bottom left is equal to the bottom left cell is equal to the top right cell, so we don't need to do any moves. So the answer for all paths would be a frozen set containing only this string. Okay, that seems correct. There's only one path from the bottom left to the top right for a grid with one row and one column. Okay, so, and that path is the empty path, right? If there are no rows or there are no columns, then there are no paths. From the bottom left to the top right, because the grid does not exist anyway. So this will catch the cases where we exceed where we try to go up if you're already at the top of the grid, or if you try to go to the right if you're already at the rightmost column of the grid. And let's try that. If you run this assertion, you should get no errors. Alright, so it was able to generate all of these. Okay, let's check the other problems. This time, diagonal movements are allowed. Let's see. So, we'll be adding, I think this is easy to fix, all paths that include diagonals. We just need to include that option here. If you wanna go up, northeast, I guess. So one row up, one column to the right. Then we simultaneously make the grid smaller, one row and one column. Okay. Let's try the assertion here. Should be able to generate all of those. Alright, it works. One more. So only movements around are up and right, but there are obstacles. So let's see. But this one needs an actual grid. So we start from the bottom left again, then you want to go to the top right. So this is a different function now. Let's call this all paths obstacles, then an actual grid. Okay. Also return a frozen set. So we're gonna do that again. We have two choices for movements. You can either go up or go to the right. So this would be similar, right? We have the same visual thinking here. Let's just replace this. Obstacles. Okay. Okay. But this would be... Sorry, no, that's wrong. This would not be R-1C. This would be the grid except except the last row. Okay, next we want the grid but the leftmost column removed, so maybe something like row everything except the first cell for row in grid. I think that works. Okay. So base cases. Okay, let's write the base cases. Okay, so assume the bottom left and top right cells don't have obstacles. If the grid contains only one cell, then there's only one path, the empty path. Otherwise, this will not work. Okay. If grid -1, 0, if we end up on a cell with an obstacle, the bottom left cell is an obstacle, we return empty frozen set. Otherwise, how should we do this? Let's account for the cases where our grid is, we cannot remove one row or one column from the grid. Okay. Say answer equals frozen set. If land grid is greater than 1, no, how do we do this? Okay, let's try this. Try these base cases. If run out of rows or run out of columns, or we end up with an obstacle, then we return the empty frozen set. Let's try. Okay, it's not working. I guess we need to check that first. Alright, it works. Ooh. So, okay. So, alright, let me go through what happened here. How do I move this? Okay, let's keep it there. So if we run out of rows or columns, or we hit an obstacle in the bottom left, then there's no path to the top right. If we end up with a grid with only one cell, then the answer is the empty path. Otherwise, we generate all paths as we make the grid smaller. If we go up, we remove the last row. If we go to the right, we remove the first column. Okay, that was a long series of problems. Alright, let's tackle a problem that is unique to this lecture. We have pattern avoiding strings. Okay. Given an integer n, how many strings of length n consisting of a, b, and c do not contain the substring ab? Let's call that function that counts that ab avoiding. For n equals 2, the answer is 8. Let's try to get that, generate those. So ab avoiding 2. What's the problem again? We will build strings consisting of the characters a, b, and c, but it should not contain the substring ab. So let's build all of those. Two characters, right? A, ab is not allowed, ac, ba, bb, bc is fine, ca, cb, cc. So we do have 8. Alright, how do you write this function now? So let's try to do recursion. Let's try to choose the first character. So, well, we have 3 options. If we choose a first, then we are solving ab avoiding, so that's ab avoiding n, right? If we choose one character, we are solving the problem with one less character, n minus 1. But there's a restriction. But b not allowed as the first character in the next one, as next character. So we have take note of this. If we choose v to be the first character, then yes, we can definitely count that with ab avoiding n minus 1. If we choose c as the first character, then yes, we can count that by using AB avoiding n minus 1 by wishful thinking. Then we just need the base case. An obvious base case would be AB avoiding 0 if the length of the string needs to be 0. There's only one way to do that, which is the empty string. So we have the following recurrence: AB avoiding n is equal to 2 instances of AB avoiding n minus 1. This corresponds to the choices B and C for the first character. But we need to add this, the AB avoiding n minus 1, but with a condition that we cannot choose B as the first character for this length n minus 1 string. So we cannot, how would we include this condition in the recursion? So instead of using AB avoiding, let's define another function. Let's call that AB avoiding A. The A here stands for we chose A as the previous first character, or the previous character. So AB avoiding A, n. This means chose A as previous character. So for this one, what are our choices to avoid having a substring AB? We cannot choose B as the first character because that would produce a substring AB. So we only have two choices. If we choose A, then we still have that problem of not being able to use B in the next character. So this is actually an instance of AB avoiding A again for n minus 1. But if we choose C, note that we cannot choose B. If we choose C, then we are free to use B in the next character. So this is an instance of AB avoiding only n minus 1. Okay, so we have two functions. Let's write those two functions down. So these are our functions. Hopefully you understood what the two functions stood for. And we can solve it like this. Where's our code? Def AB avoiding n. Let's write the base case out. Start. N is equal to 0. There's only one string that satisfies the conditions, that the empty string. So there's only one string. Otherwise, return if we chose A as the first character, that's AB avoiding A and minus 1, plus if we chose B as the first character, that's AB avoiding n minus 1, plus if we chose C as the first character, that's also AB avoiding n minus 1. Now we need to write AB avoiding A. Avoiding A. Similarly, if n is equal to 0, return 1. Otherwise, return if. So we have two choices here. We cannot choose B because that will cause substring AB to appear in the string. So if we chose A as the next character, as the first character, then we also cannot use B in the next one. So that's AB avoiding A. We chose A here as the first character. If we chose C as the first character, we go back to the case of AB avoiding. N minus 1. And does this work? Let's assert that AB avoiding 2 is equal to 8. And for AB avoiding 3 should be equal to 21. I'm not going to enumerate all of those strings. This is equal to 21. Let's see if it works. Alright, the assertions pass, but what's happening here? Look at our recursive functions. AB avoiding calls on itself and AB avoiding A, but AB avoiding A calls itself and AB avoiding as well. So these two functions call each other, depend on each other. How does this work? Isn't this circular definition? Why is this recursion working? Well, it still works because n decreases for each function call. So eventually we'll reach the base cases of either of the two functions. Okay, there are no cycles in function call dependencies. You can verify that by, let's try to draw the recursive calls for AB avoiding 2. So it calls 3 functions. AB avoiding A1 and 2 calls to AB avoiding 1. I'll just write them here. AB avoiding A1 calls AB avoiding A0 and AB avoiding 0. AB avoiding calls 2 function calls avoiding, actually 3, A0, then 2 copies of AB avoiding 0. And these are all base cases, and the recursion will terminate eventually. Okay? This is called mutual recursion. 2 functions or more calling each other to describe the recursion or the recurrence. This is also possible for more than 2 functions. Let's do this exercise. Given a sentence, extract its parentheticals. Assume that there are no nested parentheses. And assume that the input is valid, the parentheses match. So parentheticals, so all the strings inside the parentheses. So no nested parentheses and the parentheses match. Those are our assumptions. So how do we do this? So maybe mutual recursion can help. We could write parentheticals as a function that looks for the next opening parentheses, and write another function that assumes that you already found a parenthesis and it's trying to close that open parenthesis. So let's do that. Def parentheticals string. Well, base case, if the string is empty, then, well, what do we return? A tuple containing the parentheticals, right? And we return an empty tuple. Otherwise, if the first character of the parentheses of the string is equal to the open parentheses, then we pass the rest of the processing to another function. let's call that parentheticals right. Let's pass the rest of the string aside from not including uh, the opening parentheses. Okay. Otherwise, return parentheticals. We search for opening parentheses for the rest of the string. Okay. How about when we get to parentheticals are okay. Again, if the string is empty, return this. Return empty tuple. Otherwise, if we encounter the closing parentheses, how do we do this? Actually, we can make this accumulative. Let's try to make this accumulative. This is partial. If we found the closing parentheses, return. We include the partial result. No, this should be the empty string. I will build a string containing the parenthetical that we are trying to find. Let's include the partial here, and then whatever parentheticals we can still find in the rest of the string. Otherwise, we return parentheticals are for the rest of the string. So this corresponds to sorry. Partial plus S0. There we go. So what do these two functions mean? So parentheticals looks for the next closing opening parentheses. If the string is empty, then there are no more parentheticals to be found. If the first character is an opening parenthesis, then we return the result of parentheticals are, which builds the parenthetical starting at this portion of the string. So it tries to close the parenthetical. It looks for the closing parentheses and does that by cumulative recursion. Otherwise, if we've not found a starting parentheses, then we look for the parentheses in the rest of the string. For parentheticals are, it's trying to close the parentheses. So again, if the string is empty, then return nothing, empty tuple. If we found the closing parentheses, then whatever the word that we found, or the substring that we found, we include that in the results and look for more parentheticals in the rest of the string. So we are looking for a fresh opening parenthesis. This is what this means. Okay. So this will return a tuple as well, so we will splat it here. Otherwise, we return. So if we have not found the closing parenthesis yet, we will continue appending to this, or we'll continue adding to this partial string that we are building we will add the first character to that and continue searching for the closing parenthesis using parentheticals R in the rest of the string. So let's see if this works. Instead of asserting this, let's print the result of parentheticals. It's probably true. Can you see why? Let's print the result of this. You should get the tuple containing these two strings, I hope. Yes, it works. So another example of mutual recursion. Here's another one, last example for this lecture. Here's a pile of end stones. Two players, Alice and Bob, are playing and then take turns removing stones. Alice goes first. So if it's Alice's turn, she can only take away either exactly 1 stone or exactly 4 stones. If it's Bob's turn, he can take either exactly 1 stone, exactly 4 stones, or exactly 9 stones. And the loser is the player who cannot make a move because the pile is already empty. Note that both players can make a move if there are still stones because they each have a move to remove exactly 1 stone. Okay? The players are very smart and choose the most optimal moves while playing. Who wins the game? So, how do we do this? So, maybe we can try modeling the game as we'll have a function to check if Alice will win, and maybe a function to check if Bob will win given the number of stones currently. And we can formulate it like this. A game state is winning for a player if they can find a move such that the resulting game state is not winning for the other player. So after doing one move, any move that they can do, if it results in a non-winning state for the other player, then they should win, right? The base case for winning would be the base case for not winning would be if n is 0 when it's your turn. For a certain player, if that player ends up with 0 stones, then that player loses. Okay? So here's a function that describes what's happening. So we define a function. Alice wins if she's next. If Alice takes 1 stone and Bob loses, then Alice wins. Or if Alice cannot win with taking 1 stone, if Alice takes 4 stones and Bob loses with n minus 4 stones, then Alice wins. Otherwise, Alice loses. These are the only moves that Alice can do. But how do we know if Bob wins? That's another function. If Bob takes 1 stone and Alice loses with 1 stone less, then Bob wins. Return true for Bob. Bob has 2 more moves. He can take 4 stones, if that's possible. And if Alice does not win with 4 less stones, then Bob wins. Bob can take 9 stones, and so if these 2 moves don't translate to a win for Bob, then Bob will try taking 9 stones if possible. And if Alice loses with n minus 9 stones, then Bob wins. Otherwise, if Bob cannot win with any of these moves, then Bob loses. Notice that the two functions call each other, and you can simulate the game using these. Alternatively, you can formulate it like this with the chain of conditionals. Where's the base case here? Well, if all these conditions are ORed together, if all of them are false, then the answer is false. Base case is implicit. Well, the base case would be when n becomes exactly 1 and well, if n becomes 0, then all of these will be false. So for both functions, so the base case is hidden in this way. All right, let's use this formulation to test. This is pretty weird, but you can follow the logic. Okay, let's fix this code. Alright, so let's try for different values of n. And let's see what happens. Let's print. Let's check if Alice wins if there are 8 stones. Alright, Alice wins if there are 8 stones. How about 16 stones? Alright, let me copy the whole list so that I don't move through the slides every time. Okay. 16. Does Alice win with 16 stones? Okay, true. How about 24? True. How about 32? False. Alice loses apparently. If there are 32 stones, how about 40? False still. How about 48? True. How about 56? True. Oh, I think we are already seeing somewhat of a delay at 56. Takes a while to compute. Let's get the next multiple of 8, which is 64. Ooh, it's taking a while to compute. Let's try 72. And it's taking much longer to compute. So we'll see why this happens in a future lecture. Oh wow, it's taking quite long. Apparently the answer is 72. It's false for n equals 72. Okay. In a later lesson, we'll see what's happening here. But this is mutual recursion. 2 or more functions calling each other, but using recursion, but eventually the function calls lead to 1 or more base cases. Alright, that's it for lecture 10. Try to solve the practice problems that you have not solved yet. Alright, thank you for your patience. You can always fast forward these recorded lecture videos if you want, if the pace is too slow. So see you in the next one.